Hello everyone and welcome to the first video in the Python Deep Learning series in which we will be following the book by François Chollet, which is Deep Learning with Python second edition. This book is written for Keras, so that's what we will be learning. We will be starting from the very first chapter, that is what is deep learning. So enjoy the video. In the beginning, I thought it would be nice to skip this chapter, but I think it's very useful for the beginners in deep learning. So we will start with the very first chapter, which is what is deep learning. There's a lot of information in this chapter. Maybe all of that is not required for you to start with deep learning, but it's always good to know about some of the history and what's taking place these days. I have skipped those parts, but I definitely encourage you to take a look. So, what is deep learning? Before we start with deep learning, it's good to know where deep learning and machine learning and artificial intelligence lie in the form of a Venn diagram. So, as you can see, deep learning is a part of machine learning. So, it's a subset of machine learning, and deep learning both are subsets of artificial intelligence. Now we will start with some definitions of artificial intelligence. So what is AI or artificial intelligence? So it's the effort to automate intellectual tasks normally performed by humans. And it's a field that encompasses machine learning and deep learning, but that also includes many more approaches that may not involve any kind of learning. So once we know the definition of artificial intelligence, it's a huge field. We also should understand what symbolic AI is. So let's assume you're building a algorithm to play chess. So when you're building an algorithm to play chess, you will have some hard-coded or handcrafted rules, and that's not machine learning. Symbolic AI is not machine learning. It's more about having a sufficiently large set of explicit rules for manipulating knowledge stored in explicit databases. So there's too many terms here, and you don't have to know them all. So in symbolic AI, you have a set of rules, and you create rules. But these rules are only suitable for well-defined logical problems. For example, playing chess, the example that I just mentioned. So how do you use these rules? How to for more complex tasks like image classification or speech recognition? So for example, if you have a set of images which are dog images and a set of images which are cat images, how will you make a set of rules that when you get a new image, it says if it's a dog or a cat? Or for speech recognition problems and many other problems. So that's why we have machine learning. And there's a big difference between classical programming and machine learning. In classical approach, we make rules. We make a lot of rules, and machine learning algorithm is rather trained than explicitly programmed. And this system learns rules on its own. So you don't supply rules to these kind of systems. So in classical programming, the inputs are rules and data, and based on that, you get the answers. But in machine learning, the inputs are data and answers, and you get rules in the end. And when you have the rules in the end, you use these rules for different tasks. So for like, if my data here is images of cats and dogs, and my answer is cat or dog, the machine learning algorithm is going to make some rules that you can use when you get a new picture. You can use these rules to determine if this is a picture of a dog or a cat. In machine learning, we need three ingredients. So the first one is input data, which can be images, or which can be audio files, or which can be something like CSV files or tabular data or features or anything. We also need expected outputs. So once you have the input data must be associated with some kind of outputs. So these outputs are generally called labels or targets. So if you have image of a cat, it must be labeled as cat. And the third one is a way to measure if the algorithm is doing a good job. Now this is very important. So this tells the algorithm, machine learning algorithm, how good it is, or it tells us how good your machine learning algorithm is. So what is this way of measuring doing? It's trying to determine the distance between the output of your algorithm and the true labels or targets and the expected output. So what is the difference, like how far your predictions are from the expected output? And this score, the score that is returned, is used to tune the machine learning model. Now what these things mean, don't worry about it, we will learn them in near future. And the tuning step is called learning. So learning, a machine learning algorithm is learning. So this is the tuning or adjustment step. So what a machine learning model does is to transform the data into meaningful outputs. And the central problem in machine learning or deep learning is to meaningfully transform data. So this is very important word here, meaningfully transform data. That is to learn the representations of data to get the desired output. So what do representations mean? So let's see. If you have ever worked with images, if you have not, don't worry about it. But if you have ever worked with images, you know that images can be encoded in many different formats. So one of the formats is RGB, that's the most common format, which is red, green, and blue. They can also be encoded as HSV, which is hue, saturation, and value. So if you have a task which says you have to select all the blue pixels in an image, this task is much easier in RGB format because you already have red, green, and blue values. And if the task is to make the image more saturated or less saturated, it's much easier in HSV format. So these are two representations for your given task. And these formats are also known as transformations. So the machine learning models are all about finding appropriate representations or transformations for your input data. Again, coming back to representations. So let's say if you have a task which is to make an algorithm that given the coordinates of a point predicts if it's black or white. So here you can see you have a bunch of black and white points which are on this coordinate system x and y. So what you know is the values of the coordinates. So let's say x1, y1, x2, y2, and so on. So you know these coordinates, and they say like you already know if this is a black point or a white point. So you have some points and like x1, y1, x2, y2, and xn, yn, and each point has a color associated with it. So in machine learning you can call them as features, and these become your targets or input data. So you got two of the ingredients to build a machine learning model: the features or the input data and the targets. And now you need a way to measure how good your algorithm is, and that can be how many points are classified correctly. What is the percentage of points classified correctly? So if you build an algorithm and I give you like 100 coordinates, and we can check what is the percentage of the points which has been classified correctly. So that's the performance of your machine learning model. So since we are talking about representation, we can also represent this data that we have seen with a new coordinate system. So let's say we change our coordinate system. So here you can see we have a quite good separation with black and white. So in another format, we have the representation like this. So these are your new coordinates. So now you can say that if the value is x greater than 0, or the value of x is greater than 0, then it is black color. And if the value of x is less than 0, then it's white color. So now, to solve this problem, you have a new representation, which is the new coordinate system, and a simple rule, which is this one. And based on these two rules, you can solve this problem, the problem that you have. But obviously, most of the times, it's not this easy. So let's say if you have a bunch of images labeled from 0 to 9, 0, 1, 2 to 9. And so each image has one number in it, and it's anything from 0 to 9. So now you cannot make these rules very easily. So this dataset is also known as MNIST dataset, which is a very popular dataset in machine learning. And rule-based representations, they don't last. Maybe you can make some rules like, I don't know, like how many times you see loops in numbers. So these kind of rules you can make. So you have to make maybe thousands of rules, and based on these rules you can say if you have a new image what number it is, but maybe it's not going to perform very well. And it's also very difficult to maintain, because when you're creating rules, they should also generalize, and if they don't, then these rules are not very useful. And to keep the rules to keep them generalizing on new data, you have to constantly update the rules. So what machine learning does is it searches for useful representations and rules over some input data within a predefined set of possibilities, which is also known as hypothesis space, and with a guidance from a feedback signal. So in our previous example, the predefined set of possibilities is the coordinates. And the guidance from a feedback signal is the score that you get in the end, the percentage accuracy, let's say. And deep learning is a subfield of machine learning. So now we are moving to deep learning, and the book is about Python deep learning, right? So it's a subfield of machine learning, and in deep learning, we learn successive layers of increasingly meaningful representations. So in deep learning, deep doesn't mean the depth, but it rather means the successive layers of representation. And depth of the model is the number of layers contributing to the model. And in modern machine learning, you will see layers from anywhere to tens or hundreds. In shallow learning, you have one or two layers. So if we are talking about the MNIST example, where you have to classify every picture into an image, what you can do is you can take the pixel histogram and add a layer of classification on top of it. So if you don't understand all these terms like layers or pixel histogram, don't worry much about it right now. Just know that in deep learning, we are learning successive layers of increasingly meaningful representations. Neural networks, they help to learn these successive layers of representations, and neural networks are stacked on top of each other, and they do not model brain. I don't know what you have heard online, but they do not model brain, and that's what the author also mentions in the book. And it can be defined as a multi-stage information distillation process. So in every stage, you're distilling some information, and in the end, you are solving a problem. So what are the representations learned by machine learning? So let's say you have 4 different layers in which you're distilling some information. So some information will be learned by layer 1, some layer 2, layer 3, and layer 4. And in the end, you have a classification layer. Let's say this is a classification layer. And this is the same problem with MNIST. So you have an input image, and this image needs to be classified into a number. And here you see 4, and it is 4. And how do we get that output is from distilling the knowledge from each and every layer. So what do these layers do? In very simple words, these layers implement data transformation. So if you have a layer, it's transforming the input data into something and passing it to the next layer or to the classification head or the classification layer. So, and each layer is parameterized by its weights. So that's why we have weights here. So weights are nothing but a bunch of numbers that tell a layer how to transform the data, which is inputting that layer. And when we say learning in deep learning is finding the right values of weights for all these layers. And weights are also known as parameters of a neural network. So you will come across this term a lot, the parameters of neural network. In the end, the goal is to find the right values of these weights. So you have an input data, you apply some weights to it, and that's what the layer is doing. And you pass it to the next layer. Now, how to update these weights? So to update the weights, we need few more components in the neural network. That is loss function. The first one is a loss function, and what loss function does is that it calculates the deviation. So if you want to control the output of neural network, you need to measure how much the output deviates from the real target values, and that's very important because if you're predicting some random predictions, then your neural network is not good, right? So you wanted to, if you input a cat image, you wanted to predict that it's a cat. So this deviation from predictions to true targets is calculated by the loss function. And loss function is also known as objective or cost function. The loss function returns a score, and this score is then used to update the weights of the neural network. This score is usually a distance from real targets to predicted targets and tells us how the neural network is performing. So how does loss function update the weights? It doesn't. The task of updation is performed by optimizer. So you have the loss function that returns a loss score, and this loss score is then passed to the optimizer, which in turn updates the weights. So there is an algorithm called backpropagation algorithm, which is the central algorithm in deep learning, and the optimizer implements the backpropagation algorithm. So initially, when the neural network has just started learning, these weights are initialized by random values, and as it sees many different examples, so let's say you have one image coming in and it has seen that image, it has calculated the loss function, it has calculated the loss score, it passes to the optimizer, and optimizer in turn update weights. Now you have second example, and the same process is performed over and over again, and in the end these weights won't be random anymore, and the layers will be able to transform the data correctly. So in the beginning we get bad predictions because our weights are random. As we update weights, the predictions should become better. And all this adjustment is done inside something called a training loop. So that's it for the intro to AI, machine learning, and deep learning. I hope you understand how machine learning and AI, deep learning works now. And in the next session, we will take a look at one of the examples. We'll try to implement a neural network on our own. I hope you liked the video. If you did, don't forget to click on the like button, do subscribe, and do share the video with your friends. And we will see you in the next video.